Hello, this is the first part of chapter 4.7, and we're going to talk about discrete signals. And the signals are everywhere around us this day. You probably have heard about the Internet of Things, which is a way to collect the signals from pretty much any device you encounter. And in generally, we call the signal any digitized sequence. So any function which defined on an integer is called generally a signal. And today, for the example in this chapter, I will use the sound recording as an example of signal. For example, the single harmonic or simple tone is defined by the sinusoidal functions. And generally, the high frequency sound is high pitched, and the low pitched sound has a lower frequencies. And of course, that frequency is not the only important thing for the sounds. The amplitude or the height of the wave is also very important. Generally, the higher the amplitude, the louder the sounds. And again, we're still talking about the simple tones here. In a regular conversation or music or any kind of sound, there is multiple frequency present at the every given time, and this different frequency has a different intensities. So usually when the sounds are recorded, or we call it the digitizing the sounds, we are working with the for every moment of time. Each frequency of the sound is basically represented by its intensity. You probably saw the bar like this on any sound processing software you can find these days. So each single bar here represents a given frequency. And the higher the bar, the louder is the sound at this frequency. And yeah, for example, here, these three frequencies are probably represent like very loud beat, and here over there like the frequencies is like you can barely see the height, so this is basically unused frequency. So an important property of the signal, as we saw in the previous examples, are linear dependence. So basically we said when the several signals are linearly independent, when their linear combination is equal 0, only when all the weights are equal 0. Using the example of the sound over here, we can interpret it as if we have these three frequencies, say, yeah, not exactly the most exciting sound, but say 3 frequencies. And this sound will be equal 0, or you will hear nothing, only when intensity of all 3 frequencies equals 0. So when the signals are linear independent, there is no fancy frequency cancellations. All 3 frequencies has to be equal 0 to give us a silence. But of course, sound does not exist at the one given moment of time. Sound is like the varies with time. So we can write down this linear dependence equation for the any moment of time. Say if k represent the current time, k plus 1 will be the sound at the next system, next second. And in the next second, our system should also be linearly dependent. So linear combination of our signals u, v, and w at the current time k plus 1 second should be also equal 0, only when all c equals 0. And we can write it down for 2, 3 seconds, 3 seconds, as many seconds as we want. And the best way to organize this system now, which has a lot of equations with a lot of weights, of course, is a matrix multiplied by the vector. So we put our signals in the neat rows, signal u, v, and w, and multiplied by the vector of weights c1, c2, and c3. And again, because we are trying to figure out if our system is linearly independent, their linear combination should be equal 0. And this matrix is very important. Obviously, we want to write down the linear combination for any number of signals. We call it the Kasarati Matrix, and it's commonly used to analyze the signals. And of course, since we're talking about linear combination, we can always invoke our invertible matrix theorem. And remember that the linear combination property and invertibility goes together. So if matrix is invertible, then our matrix will be linearly independent, or our signals will be linearly independent. Okay, so let's just try to identify linear independence for this rather simple signals. The first signals is just number 1 in the power k. Thinks about as a time, the k representing the time, for example, if it's confusing to you. But generally, k is what we call a step, and it can be any integer, positive or negative. The second signal will be -2 in the power k, and the third signal will be 3 to the power k. And just to kind of illustrate, here is the short trace. We're going from the step or value of k from -4 to 1. And for our first signal, of course, it's a straight line, and -2 is equal to k is oscillate, and 3 in the power k goes up. Okay, so let's write down our Kazarati matrix for this system. And again, we just take our first system, 1 to the power k, and now write it down for 3 steps, k, k plus 1, and k plus 2. And again, we organize it as a columns. And we repeat for our second signal, -2 to the power k. Again, we just put the multiple indices in the columns, and the same for the 3 to the power k. So basically, if this matrix is invertible for any k, we can conclude that our signals are linear independent. And it's just easy here to choose one value of k, and because I like things simple, I'll choose k is equal 0. So the first row will give us 1 to the power 0, 1, and 2, which of course will remain the 0. The second will give us k to the, again, 0, 1, 2. But now because we put raise -2 to the power k, our second entry would be negative. And we repeat for the 3 in the power 0, 1, and 2, and get this matrix. So now again, we're going for linear independence. So of course, we will try to reduce it to the echelon form and see if it's consistent. Okay, let's try to reduce, put the first column in the echelon form, the second one. And this seems to be a pretty good news. Over here, we have all 3 pivot columns. That's nice, which means that our matrix is invertible for k is equal 0, and since the matrix is invertible, we can confirm that these 3 signals are linearly independent. Okay, now I would like you to go to the end of the chapter 4.8 and try to practice a couple of more examples for linear independence of the signals.